So welcome to the new session of Theory of Computations. Today, the topic of discussions will be 2 DFA, unreachable states and dead state. So objectives, after going through this topic, you should be able to define two-way finite automata, understand the concept of unreachable state, know about dead state. So first of all, two-way finite automata, or you can say that 2DFA. So in two-way finite automata, the tape head can move left or right direction. In all automata that we have studied, discussed, allows their tape head to move in right direction. But two-way finite automata remove this limitation by allowing its tape head in both directions. If you remember the definition of finite automata is having 5 tuples Q, sigma, delta, Q naught and F, right? And the block diagram for finite automata is this. We have one tape head which is divided into n number of cells, and your tape head is connected to reading head, right? This is your reading head, which moves in the right direction, which moves in one direction, that is right direction. But what is the difference between DFA and 2DFA? In 2DFA, your reading head will move towards left and as well as towards right direction, right? Which means that it will move in both the directions. This is your 2DFA. So the same tuples will be there, that is Q, sigma, delta, Q naught and F. So here capital Q is a non-empty finite set of states written with Q naught, Q1 and so on up to Qn. And sigma is a finite non-empty set of input symbols, or you can say that alphabets. So this is your input symbols or alphabets. Delta is a transition function. Delta is a transition function which maps Q into sigma goes to Q. This is the delta for finite automata. Q into sigma goes to Q. By attaching L comma R, this is the transition function for two-way finite automata, or you can say that 2DFA. L comma R. Here Q is your current state. This is your current or present input. This is your new state, or you can say that next state, or this one is your direction, left or right, left or right. So Q into sigma goes to Q into L comma R, where Q naught is the initial state and capital F is the final state. So I am repeating again, two-way finite automata is an automata in which your tape head can move in both the directions. either it will move to left direction or it will move to right direction. It is of 5 tuples Q sigma Q naught F delta, where capital Q is the finite non-empty set of states represented with the help of Q naught, Q1 and so on up to Qn. Then we have sigma, finite non-empty set of input alphabets, or you can say that symbols. Then we have delta. Delta is a transition function which will be written with the help of Q into sigma, which will be written with the help of Q into sigma goes to Q into L comma R. So this is your delta in case of 2 DFA, right? Then Q naught is the initial state and F is the final state. Next definition is, let's take an example. If delta Q naught comma B is equals to Q1 comma R, right? In case of 2 DFA, your moves will be of the form of this. Let me discuss it with you. So again, I am comparing the moves of DFA with 2 DFA. In case of DFA, we have delta Q1 comma A is equals to Q2. This is in case of DFA. But in case of 2 DFA, your moves are of the form of delta Q1 comma A is equals to Q2 comma R. Q2 comma R. This means that upon the processing of A, Q1 is moving to state Q2 and the direction of motion will be right direction. Right? Let's take one more example. That is delta Q naught comma A. It is equivalent to Q2 comma L. This means that upon the processing of A, Q naught is moving to Q2 and the direction of motion will be left. The direction of motion will be left. So here is the explanation of first example. On reading symbol B on state Q naught, that 2 DFA moves to the new state Q1 and move the tape head 1 square to right. Similarly, if delta Q naught comma A is equals to Q2 comma L, it means that on reading symbol small a, when you are in Q naught state, the 2 DFA moves to the new state, that is Q2, and move the tape head 1 square to the left. So these are the examples which belongs to 2 DFA. The next definition is for unreachable states. So unreachable states are the states that are not reachable from the initial state of the DFA. For any input string, these states can be removed. Right? So consider the example given in the PPT here. You can see that from the initial state, that is capital S. Capital S is the initial state as well as your final state, right? here capital A is also acting as your final state. So when you start from capital S, upon the processing of any input, you can't reach on C. Here you can see that you don't have any edge which will take you to C state, right? So in above finite automata, we have unreachable state C because on any input from the initial state, we are unable to reach that state. This means that this state is useless. So we eliminate this type of state while minimizing the automata. The very important concept, minimizing the automata. So whenever we are going to do the minimization, your first step is to remove the unreachable state. So let me draw one more example on the board regarding unreachability. So suppose Q naught upon the processing of A, it is going to itself. Upon the processing of B, it is going to Q1. Q1 upon the processing of A, comma B, it is going to Q2, and Q2 is your final state. So here I am introducing one more state, that is Q3, right? Q3 upon the processing of A, it is going to Q1. So here you can clearly see that Q3 is the state where we can't reach. So we don't have any input string which will take you to the Q3. We don't have any incoming arrow towards Q3 from the initial state. So here Q naught is your initial state and Q2 is acting as your final state. So Q3 is unreachable state. Q3 is the unreachable state. So next definition is dead state. A dead state is non-accepting state. Accepting state is the final state, but non-accepting state means that it is a intermediate state, or you can say that it is a non-final state which goes to itself on every possible input symbol. So I'm repeating the definition again. A dead state is an non-accepting state which goes to itself on every possible input symbol. Once the machine enters a dead state, there is no way for it to reach an accepting state. So we already know that the string is going to be rejected, right? So in other words, dead state is also called a sink state, or you can also call it as trap state, trap. So it is one from which we cannot escape, that is, it has either no transitions defined or transitions for all symbols goes to itself. So here you can see the diagram. So initial state is capital A, final state is capital B. You can see that upon the processing of A, comma B, because here we have two inputs, 0, 1. We have two inputs, 0, 1. So A is acting as your initial state, B is acting as your final state. So here C is the dead state because for every input symbol, transition ends on them, right? So you can also say it as transition for B also ends on them, but B is your final state, but Z state is only the known final state, right? So let me clear this point to you. So let me show the example for dead state, sync state, or trap state. So first of all, a dead state is a known final state. So here Q1 is the initial state. Upon the processing of A, B, it is going to Q2, and Q2 upon the processing of A, it is going to Q3. Upon the processing of A, B, it is going to itself. So here we have one more state, that is Q. So here you have a B, right? So Q naught upon the processing of A, it is going to Q3. Q2 upon the processing of B, it is going to Q4. And Q4 is acting as your final state. Upon the processing of A, B, it is going to itself. So here you can clearly see that Q3 is the state which goes to itself on every possible input symbol. Every possible input symbol is A, B, and it is your known final state, or you can say that known accepting state. Known accepting state is known accepting state or known final state, or you can say that intermediate state. Only these states will be your dead state. So here Q3 is your dead state. Once you enter into Q3, you will not escape. Once you will enter into Q3, for example, let me process the string A, B, right? So Q1, upon the processing of A, it is going to Q2. Q2 upon the processing of next A, it is going to Q3. Q3 upon the processing of this B, it is going to Q3 itself. After that, whatever the symbol you are facing, it will be taking you to the Q3 state only. Now you have been escaped, you have been trapped into the Q3 state. This means that Q3 is your dead state, or you can say that trap state, or you can say that sync state. So next topic is minimization of DFA, deterministic finite automata. So objectives, after going through this topic, you should be able to define the minimization, understand the procedure for minimization, and have some hands-on with various examples. So first of all, the definition. Minimization of DFA means reducing the number of states from given FA. Thus, we get the finite state machine with redundant states after minimizing the finite state machine. So the procedure involves 4 steps. Step number 1, identify unreachable state if any. Step 2, derivation of values. Step 3, construction of new transition table. Step number 4, construction of new transition diagram. So I am repeating the procedure one more time. Step 1 says that you have to identify the unreachable state if there is any unreachable state present in your diagram or table which is given to you. Number 2, you have to drive the values in the form of pi naught, pi 1, so on up to pi n. Number 3, you have to construct a new transition table after the minimization, right? And number 4, you have to construct a new transition diagram. So note, minimization is possible for DFA only. Remember this point. You have to minimize the DFA only. If you will be given with NDFA, then it needs to be converted into DFA first, then its minimization is possible. So proceeding towards first example. So here you will be given with either a table or a diagram. So in this case, a transition diagram is given to you, and for this transition diagram you will have to construct a minimum state automata equivalent to the finite automata given in the form of transition diagram, right? So first of all, you have to make one transition table because we have to derive some values, and in the derivation of values the comparisons are easier in case of transition table as compared to transition diagram. So your first step is to draw the new transition table, draw the transition table from the given diagram, So let me draw this table on the board. So first of all, so here we have two inputs, 0, 1, and we have some states in the form of Q naught to Q7. Q naught is initial, Q1, Q2, Q3, Q4, Q5, Q6, right, and Q7. And the last state is Q7. So here is your Q7, right? So I am drawing this table from the given transient diagram listed in your PPT, right? So first of all, you have two inputs in the form of 0 and 1. Q naught upon the processing of 0, it is going to Q1. Q naught upon the processing of 1, it is going to Q5. Q1 upon the processing of 0, it is going to Q6. Q1 upon the processing of 1, it is going to Q2. So here Q2 is your final state, circle it. Then Q2 upon the processing of 0, Q2 upon the processing of 0, it is moving towards Q0, and upon the processing of 1, it is going to itself, that is Q2. Next, Q3 upon the processing of A, Q3 upon the processing of 0, it is going to Q2, and upon the processing of 1, it is going to Q6. Next we have Q4. Q4 upon the processing of 0, it is reaching to Q7, and upon the processing of 1, it is going to Q5. Next we have Q5 upon the processing of 0, it is moving to Q2, and Q5 upon the processing of 1, it is moving to Q6. Next we have Q6 upon the processing of 0, it is moving to itself, and Q6 upon the processing of 1, it is moving to Q4. Last state is Q7. Q7 upon the processing of 0, it is moving towards Q6, and Q7 upon the processing of 1, it is going to Q2. So here your transition table is completed, right? So this table we have just made. Let me check, is it correct? So we have Q1, Q6, Q0, 2, 7, 2, 6, 6, right? 5, 2, 2, 6, 5, 6, 4, 2, right? It's exactly the same table which I have just drawn on the whiteboard, right? So after drawing the table, your step number 1 says that you have to find out the unreachable state, if any. So step 1 is you have to find the unreachable state. From the diagram, you can clearly see that. From the diagram, you can clearly see that here Q3 is the state where you can't reach, right? So you don't have any edge starting from the initial state which will take you to Q3 state. So here Q3 state is acting as a unreachable state. So this is the concept with the help of which you can find unreachable state in your diagrams. Then how you can find the unreachable state from your table? Let me show you. So from the table, you have to check that all the states which have been listed in column number 1 have also been listed in column number 2 and 3, right? So this is your column number 1, this is your column number 2, this is your column number 3, right? Column number 1, 2 and 3. So column number 1, column number 2, column number 3. So here you can see that Q0 is your initial state which I have written here. Q1. So here you can find the state Q1. Next state is Q2. So here you can find the state Q2. Next state is Q3. So neither in column number 2 nor in column number 3 Q3 have not been listed. So the first unreachable state which we have identified from the table is Q3, unreachable state is Q3. Next, Again Q4. So Q4 is written over here. Next Q5 is also written. Q6 is written. Q7 is written. That's it. It means you have to eliminate. What you have to do? You have to eliminate this Q3 state along with its transitions. Right? So your table will become this. After the elimination of Q3 state, your table will be of the form of this. So this is your step number 1. Then step number 2 says that derivation of values. Step 2, derivation of values. So your first value is Q1 degree. So Q1 degree is a collection of your final states. So in Q1 degree, you have to write all your final states. So here we have only single final state, that is Q2. So only Q2 will be written over here. Next we have Q2 degree. Q2 degree. So accept final state, all the remaining states. All remaining states will be written. So what are those states? The first one is Q naught, Q1, Q2 is already written and we have eliminated Q3. So Q2 and Q3 will not be written. After that, Q4, Q5, Q6 and Q7. So this is a set which belongs to Q2 degree. So after this, the derivations of pi naught, pi 1 and so on up to pi n will be continued, right? So first, pi naught. Pi naught is equals to combination of Q1 degree and Q2 degree. So pi naught is your combination of Q1 degree and Q2 degree. Here Q2, comma Q naught, Q1, Q4, Q5, Q6 and Q7. So this is your pi naught. Next, the construction of pi 1. Whenever you need to construct pi 1, you have to look into pi naught. You have to check the comparisons in pi naught. First of all, you need to write those sets. Now what you have to do? We are going to bifurcate this set. We have to reduce these states because in first state only one state is there, but in case of second set, this is one set, this is second set. In this set, more than two states are there. 1, 2, 3, 4, 5, 6. So you have to reduce this set, right? So first of all, in pi 1, you need to write those set which is having only one value. So here Q naught is the set which is having single value. After that, you need to start with comparisons. How you are going to do this? By comparing the first state, that is Q naught with all the remaining states, right? So Q naught will be compared with the Q1, Q naught will be compared with the 4, Q naught with Q5, Q naught with Q6, and Q naught with Q7. I'm repeating it again. Phi 1 is you have to write that set which is having single state. So this is your set which is having single state. After this, you need to compare Q naught. After this, you need to compare Q naught with the Q1, Q naught with the Q4, Q naught with the Q5, Q naught with Q6, and Q naught with Q7. When you are comparing, if that states are contradicting, make one new set. If those states are not contradicting, write those states in a same set. Right? So let me start with the concept. So first of all, here my first comparison is between Q naught and Q1. So Q naught and Q1, Q naught upon the processing of 0, it is going to Q1, and Q1 upon the processing of 0, it is going to Q6. So now you have to check that Q1 and Q6 belongs to same set. Yes, Q1 and Q6 belongs to same set. Let's check the second value. Q naught upon the processing of 1, it is going to Q5. Q1 upon the processing of 1, it is Q2. So here Q2 and Q5 in different set. Q5 is written here, but Q2 is listed here. So Q naught will be written here and Q1 will be written in the separate set. I'm repeating it again. First of all, you need to compare Q naught with Q1. Q naught with Q1. So you have to check both the values. So Q1, Q naught and Q1, 0. Upon the processing of 0, it is going to Q1, Q6. So Q1, Q6 is in same set. But the second value, that is Q5 and Q2, is not listed in the same set. So Q1 will be written, Q naught will be written in separate set, and Q1 will be written in separate set. Let's compare the second value, Q naught with Q4. So Q naught, Q4, 1 and 7, Q1 and Q7. It is in same set. Q1 and Q7, it is in same set. The next value is Q naught, Q4. The second value is 5 and 5. The value is same. So it means it is again in the same set. So Q4 will be written with Q naught because both the values are in same set. No contradiction. And we have created this set for contradictory states, right? So next comparison is between Q naught and Q5. Q naught with Q5. So Q naught, Q5. The first value is Q1 and the second value is Q2. So you clearly see that Q2 is in separate set and Q1 and Q2. Q2 is in separate set and Q1 is in separate set. This means that Q5 is also creating contradiction. So write in another set. Next comparison is between Q naught to Q6. Q naught to Q6. So Q naught, Q6, 1, 6, same set. 1 and 6 is in same set. 5 and 4 is in same set. So Q6 is also written along with Q4. The last comparison is Q naught with Q7. Q naught with Q7. So Q naught, Q7. The first comparison is 1 and 6. It is in same set, but 5 and 2. It is not in same set. It means that your set is completed and Q7 will be written over here. Your pi 1 is not completed yet, right? So till this point you are okay, but again you have to make comparison between Q1, Q5, Q1 and Q7 because this is a set with contradictory states, right? So Q1, Q5, Q1, Q5. So here 6 and 2. 6 and 2. 6 is here and 2 is here. Again, here you can write Q1 and Q6, Q5 will be written in separate set because it is contradictory. Next comparison is between Q1, Q7. So Q1 is there, Q7 is there. Q6 and Q6, same value. There will be no contradiction in this case. 2 and 2, again, no contradiction. So Q1, Q7 will be written. So this will be eliminated and Q5 single state set, it will be written after this. So your pi 1 is completed. So now I am going to construct pi 2. So now you have to check the pairs in pi 1. So first of all, in pi 2, you need to write those states which is having only single value. So Q2, comma, Q5. After that, you have to reduce the sets which is having more than one value. So Q naught will be compared to Q4. Q naught will be compared with Q6. Similarly, Q1 will be compared with Q7. So let me start with the comparisons. So Q naught, Q4. So here is your Q naught and this is your Q4. Upon the processing of 0, it is going to Q1, Q7. Q1 and Q7, it is in same set. So first, no contradiction. Second value, 5 and 5. Again, the value is same. So no contradiction will be there. So you can write it as Q naught, comma, Q4. So this is completed. The next comparison is between Q naught and Q6. Q naught, Q6, 1 and 6. 1 and 6 is not in same set. 1 is in another set and 6 in another set. It means that Q6 will be written in separate set because it is creating contradiction. So it will be written in separate set, right? So last comparison is between Q1, Q7. Q1, Q7, 6 and 6, same value, no contradiction. 2 and 2, same value, no contradiction. So here you can write it as Q1, comma, Q7. So here again we have to construct the pi 3 because our values are not matching. You have to continue with this method until you will get pi n plus 1 equal. So right? So next we have construction of pi3. Again, write those states which are single. Q2, Q5, Q6. Next, comparisons between Q0, Q4 and Q1, Q7. That's it. So compare Q0, Q4. Q0, Q4. First value is 17. So 17 is in same set. While constructing pi3, you have to check the comparisons in pi2. Right? So Q0, Q4's first value is 17. So same set. 5 and 5, same set. So no contradiction is there. It means you can write Q0, Q4. Right? So next, last comparison is between 1, Q7. So Q1, 6, again 6, same value, no contradiction. 2, 2, same value, no contradiction. It means Q1, Q7. So here you can see that the entire value of pi3 is equals to the entire value of pi2. It means that therefore pi3 is equals to pi2. So further minimization is not possible. So here you can clearly see that when we have started, we have 1, 2, 3, 4, 5, 6, 7. A total 7 states are there. But after minimization, now we have 1, 2, 3, 4, 5 states. So we have reduced 2 more states. So after this, step number 3rd is you have to construct a new transition table with these states, right? So write these states in square bracket. Always start with the state which is your initial state. So Q0, Q4 is acting as your initial state. After that, you can write any state of your choice, right? So next we have Q2. Next we have Q5, and last state is Q6. So here Q2 is your final state, so circle it, right? What we have done till now, you have in step number 3, make one new transition table and write these states in square brackets, right? So now how to complete this table? How to complete this table? So Q note upon the processing of 0. This is your original table. This is your original table. Look into this table and so Q note upon the processing of this 0, it is going to Q1. So here you can write it as Q1. Q4 upon the processing of 0, it is going to Q7. So here Q1 and Q7 is in same pair. So that's it. After this, Q naught upon the processing of 1, Q naught upon the processing of 1, it is going to Q5, and Q4 upon the processing of 1, it is going to Q5, and Q5 is single state. So write Q5 over here. Next, Q1, Q7. So Q1 upon the processing of 0, it is going to Q6, and Q7 upon the processing of 0, it is going to Q6, and Q6 is alone. So right, Q6 there. Next, Q1 upon the processing of 1, it is going to Q2, Q2, and Q7 upon the processing of 1, it is going to Q2. So don't need to repeat it, just write Q2. Next we have Q2 upon the processing of 0. So Q2 upon the processing of 0, it is going to Q0. But Q0 is having pair with Q4. So you need to write Q4 as well. I'm repeating again. Here you have only single state, that is Q2. Q2 upon the processing of 0 in original table, Q2 upon the processing of 0, it is going to Q0. But Q0 is having pair with the Q4, so write Q4 as well. Next, Q2 upon the processing of 1, it is going to Q2. Next, Q5 upon the processing of 0, it is going to Q2. Q5 upon the processing of 1, it is going to Q6. Last, Q6 upon the processing of 0, it is going to Q6, and Q6 upon the processing of 1, it is going to Q4, but Q4 is not alone. So again, you need to write the pairs. So your table is new transient table is completed. So after this, you have to construct the new transient diagram for this, right? So you have to construct the new transient diagram. So let me complete this. So first state is Q0, Q4 upon the processing of 0, it is going to Q1, Q7. Right? Next, upon the processing of 1, it is going to Q5. Next, Q1, Q7 upon the processing of 0, it is going to Q6. Upon the processing of 1, it is going to Q1. Here Q2. So here Q2 is your final state. Double circle upon it. So two rows have been completed. Next is Q2 upon the processing of 0. It is going to this state. And upon the processing of 1, it is going to itself. A loop is there. Next, Q5 upon the processing of 0, it is going to Q2. And upon the processing of 1, it is going to this state. Next, last row, Q6 upon the processing of 0, it is going to itself, and upon the processing of 1, it is going to this state. So this is your new transition diagram for the given table. So let me show you the PPT again. So this is your original question, the diagram. After this, we have drawn the table and we have removed this Q3 state because it is acting as a unreachable state. After that, we have done this derivation of values, right? Then this table, upon the right hand side, you can see on the board this table and the final diagram, right? So you can clearly see that in the new transition diagram, you have 1, 2, 3, 4, 5 states where Q0 comma Q4 is the initial state and Q2 is acting as your final state because it is having double circle, right? So this is the concept of minimization of automata. In the minimization of automata, you can also come up with the same number of states as you have started initially, right? So this is not compulsory. You are getting the reduced automata always. You maybe come up with the same number of states which you have started, right? So we will be covering this second example in our next lecture.